In Learning Target 5, we're talking about continuity at a point. All right? So function is continuous if all the three following conditions are met. One says f of c is defined. That means if I'm looking at some function, I have f of 3, I can put 3 into the function and I get an answer. All right? So f of c has to be defined. Then the limit as x approaches that value for that function has to exist. Okay? So the limit has to exist there. And then the limit has to equal whatever the function value was. So they have to be the same. We're going to use this definition towards the end today with our examples. Okay? That's what continuous means. So to look at some pictures to help you out with that, here are examples where you have functions that are not continuous or discontinuous. Okay? Discontinuous means there's a hole or a gap or something. So here, there's no function value there, so there's a hole, so that's discontinuous. Here, the limit doesn't exist because from one direction you approach one value and from one direction you approach the other. So there's this gap, weird situation where they don't meet up. So again, that would be discontinuous. And then here we have a hole, and then we have a different value, and since those don't match, those aren't the same, right? The limit as we approach that value is not the same as the function value, then that would also be discontinuous, all right? So functions that are discontinuous have holes and gaps and that kind of stuff that we've been looking at. So here's an example of a graph. You did this one for homework. You had to do the right hand and left hand side limits and then the limit. And so we're going to look at the continuity of the function here, okay? So we're talking about limit as x approaches -2, all right? Now, if we approach from the right, we approach 2. If we approach from the left, we approach 2, right? And so then as we approach -2 from both sides, we also approach 2, okay? So all those limits yesterday were all equal to 2. However, we're talking about the continuity, all right? The function has a discontinuity or is discontinuous, whichever you prefer to write, at x equals -2 because, according to our definition back here, f of -2 has to exist, the limit has to exist, and they have to be equal to each other. Well, the limit as x approaches -2 of the function is 2, we decided. But that has to equal f of -2. Well, at -2, there's a point right here. And that equals 3. And 2 doesn't equal 3, right? So that's a problem. So there's a discontinuity or a discontinuous at x equals -2. Does that make sense? We need the limits. We could find those, but since the limit doesn't match what the value is at that c equals -2, we have a discontinuity. Just like in this picture. The limit exists, but there's a different point, and so they don't match up, so that is a discontinuity. Okay? So the first part of your assignment today is just look at those graphs from yesterday and decide if there's a discontinuity or not. Now, there's two different types of discontinuities. There's removable discontinuities and non-removable discontinuities. Okay? Removable discontinuities means that you can somehow fill in the hole in the graph by redefining it, or maybe using algebraic methods. Okay? There's also non-removable discontinuities, which means you can't do anything about it. So looking at our pictures here, this might be a removable discontinuity. Maybe we go out and rid of some holes and gaps by factoring or doing something with the function, and then it kind of goes away, right? We find something that's equivalent. Here we have a non-removable discontinuity. There's no way we could redefine this. They're both approaching different places, so we can't redefine that. And then here we might have a removable discontinuity. Again, if I knew the function and I could redefine it somehow, then maybe I could have a removable discontinuity. So let's talk about those two types. I've got three examples. All right. Let's find the x values, if any, at which f is not continuous. Which of the discontinuities are removable? There's always going to be a discontinuity wherever the denominator is 0. Okay? So looking at the first example, is there any value for x that you could put in that would make the denominator 0? The answer is no. Okay? I can put any value in for x because I'm going to square it, which makes it positive. Then I'm going to add 1. And so I'm never, ever, ever, ever going to get a fraction with the denominator of 0. So because of that, on this question, there are no discontinuities. Or you could say the function is continuous for all real numbers. Okay? All right, on the next one. Again, we're looking for places where we put values in for x to get a denominator of 0. So looking at this function, are there any values that I could substitute in for x that would cause me to have a denominator of 0? Yes, there are. There are 2. X equals 3 and x equals negative 3. If I put 3 into the function, I get 3 squared minus 9, and 9 minus 9 is 0. So I'd be dividing by 0. That would be a discontinuity because that'd be a whole or something. That'd be weird. That'd be bad. If I do negative 3 squared minus 9, that's 9 minus 9, which is 0. I'll be dividing by 0 again. That's bad. So we have 2 discontinuities. Now we need to figure out, are they removable? If I'm looking at this function, if there's a way I can rewrite it or simplify it or find something that's equivalent, then I can maybe find something that's removable. So for this function, the denominator can be factored. That's a difference of 2 squares. So x squared minus 9 is the same thing as x minus 3, x plus 3. Well, then the x minus 3 factors cancel out. And you have 1 over x plus 3. Okay? Now, that means we have removed 1, but we have left 1. So now, which of these 2 numbers still makes the denominator 0? Negative 3 plus 3 is 0, right? So negative 3 still makes the denominator 0. So because of that, I have 2 different discontinuities. X equals 3 is a removable discontinuity because we got rid of those factors, and so now I don't have to worry about it anymore. And x equals negative 3 is a non-removable discontinuity. All right, so on the homework, you have to decide, are there any discontinuities? Is there something that's going to make the denominator 0? Or if you aren't sure, then if you look at a graph, you can always look at a graph. Okay? Here we had 2, but we can factor, so we can get rid of a factor, and then we've removed a discontinuity using algebraic methods. Okay? So you're thinking about, okay, what's going to fill, how can I change this to fill in the gap or the hole? And then you can figure out if you have removable or non-removable discontinuities. All right, one more example. This one's a piecewise. That's why I wanted to bring it up. So if I could draw a quick graph of this if you wanted me to. So y equals, or f of x equals x for all x less than or equal to 1. that means that y equals x. So if x equals 1, y equals 1. If x equals 0, y equals 0, etc., etc. For all x less than or equal to 1, so I've got a line going this way. For all x greater than 1, I have x squared. So 1 squared is 1, and 2 squared is 4, and 3 squared is 9. So I have a parabola piece right there. Okay? So if we're talking about discontinuities, again, you're looking for gaps or holes. And maybe you don't want to spend the time to graph all these. So maybe you want to do this algebraically. If we go back to the very beginning, if there's a function value defined and the limit exists, and they're both the same, then we have a continuity. If not, we don't. So it looks like on this graph that there are no gaps or holes. So it looks like everything meets up. We're only concerned about the place where they're going to connect. We're only concerned about what's happening at 1. So what's happening at x equals 1? All right. Well, if I am finding f of 1, I will be using this part of the function because it says greater than or equal to. And so f of 1, I put that into the equation. Again, the equation is y equals x. Then y equals 1. Right? The function value is 1. If I start looking at the limits, I need to look at the limits from both sides because we have two different pieces. So I need to look at the limit as x approaches 1 from the right, limit as x approaches 1 from the left, and see what's happening there. Are they the same? Well, so the limit as x approaches 1 from the right, from this direction, it's approaching 1, right, because they're following this function. From the left, or coming this way, so we're following this function, it's also approaching 1. So then it looks like, since the limits from both sides match up, that the limit as x approaches 1 is also 1. So I'm saying the limit as x approaches 1 equals the function value. So that means that x equals 1 is not a discontinuity because they meet up. So the function is continuous for all real numbers. Right? If you didn't have a graph, you have to do all this stuff. No graph. All right? We have to make sure that the function value equals the limit value. If we do have a graph, it's a lot easier to see. If you just look at it, you can see that they meet up. There's no holes or any gaps or anything, so you can tell it's continuous. All right? So 2 ways to do that. Look at a graph or use the definition. But make sure you understand that the discontinuity is only going to occur where the transitions are in the piecewise function, unless one of your functions has something weird that's going on with the denominator. Okay? So that's learning target 5. You're just looking at continuity. You're looking for gaps and holes. Is the function continuous or discontinuous? If it's discontinuous and you have an actual function, not just a graph, then you should be able to rewrite it like we did here, hopefully. So you can get rid of some of the discontinuities and call them removable again. You want to identify which is which. This is very important. Okay? That's learning target 5.